Greetings and welcome to College Algebra, Chapter 1, Section 5, where we will be talking about quadratic equations. In this video, I'm going to use these notes, which were adapted from Blitzer's College Algebra 5th edition book, and I'm going to talk a little bit about concept, as well as working through the mechanics of some problems involving quadratic equations. A quadratic equation is of this form, if I can get my pen to work, of this form right here. Still not working? Come on now. How about that? There it is. ax squared plus bx plus c equals 0. And the equals 0 part is something that I feel like a lot of us are hesitant to create. Taking an equation that has an x squared term, an x to the first power term, and a constant term, that's the c value, and balancing everything over to one side so that it's equal to 0. But we'll be doing some of that in this video, and be very mindful of the zero product principle, which says that if you're multiplying two numbers together, or if you want to multiply two numbers together and have the result be 0, then you must figure out a way to force the first or second number, in this case a or b, you've got to force one of those or both of those to equal 0. Not at the same time, but just eventually one of them needs to equal 0, one at a time. And solving a quadratic equation by factoring is a process that a lot of us do not like. However, we're going to go through some practice problems and do some factoring. As a matter of fact, let's just get right to that. This problem involves a quadratic equation, but it's not set equal to 0 just yet. So let's do the first step and set it equal to 0. So we'll keep the 4x squared minus 13x. We'll add 3 to both sides so that it's equal to 0. Great. Now, one of the big challenges in factoring arises when the coefficient on x squared, the a value, you might say, is something other than 1. In this case, it's a 4. If you could divide the entire equation by 4 in order to sort of cancel out the 4 and turn it into a 1, that would be great. Unfortunately, in this problem, the negative 13 and the positive 3 are not divisible by 4, so it's not really a good option. There's a process called the AC method, which is a little bit labor intensive. However, if you're working with a quadratic equation like this, and it is factorable, then the AC method will take you to the correct answer every time, and in the same number of steps consistently. So let's try the AC method. Remember that this equation is of the format ax squared plus bx plus c equals 0. Good, so we've got things organized for starters. My a value multiplied by my c value is 4 times 3, which is 12. You could call this your AC number or your grouping number. I'm going to use this number, this AC number, 12, and I'm going to make a list of what I call factor pairs. Pairs of numbers that multiply together to equal 12. And do this in an organized way. 1 times 12, so I'm starting with the lowest number on top, the 1. And then I know that 2 times 6 also equals 12. 3 times 4 equals 12. And then I could write 4 times 3, but that's really the same pair as 3 and 4. So I'm going to let go of those. You should be aware, however, that if the number on top is positive and the number on the bottom is positive, a positive times positive makes positive. The 12 is positive, so that's perfect. We like that. If the number on top were negative and the one on the bottom were also negative, negative times negative makes positive, so we need to consider the possibility that maybe negative 3 times negative 4 is the correct pair or factor pair that we're going to choose. how is it that I'm supposed to choose the correct factor pair? The answer is you want to choose the pair that adds to equal your b value. In this case, the b value is negative 13. So I'm going to choose negative 1 and negative 12 because they multiply to equal positive 12, but they add to equal negative 13. And if you want to pause the video and take a moment to write yourself a note as to why we have chosen that pair, then again, we chose it because negative 1 and negative 12 multiply to positive 12, but they add to negative 13. What do I then do with those two numbers? I'm going to do what I call splitting the middle term. I'm going to change the negative 13x into a negative 1x minus 12x. So you're seeing the 4x squared is staying the same, and then I'll write minus, if you want to write the number 1, it's not a bad idea, minus 1x minus 12x, that way you can see the two numbers from the factor pair that you chose, and then the positive 3 is still there. And it's still that same equation, so don't forget to bring the equals 0 with you. Great, I had 3 terms in my original equation, now I've got 4 terms. We've gone from bad to worse. Don't worry, I've got everything under control. The next thing we're going to do is do some grouping. And notice the way I'm putting these, I call them under brackets. Don't do your grouping with parentheses. Use these weird looking brackets that go under the terms. And the thing that's very important here is that this second bracket includes the negative in front of the 12. I want to make sure that that minus sign to the left of the 12 is included in my second group. It seems a little overly particular, but as we're training our eye to help our mind see this process, being very precise and organized on paper will be helpful. Okay, so we did some grouping there. Now we're going to factor inside of each of those two groups. So we could put factor and factor. In the first group, we're going to take out the greatest common factor, which in this case is just x. So I'll factor out the x, or reverse distribute it, if you want to think of it that way. And I can tell that I factored correctly by distributing the x, just doing it in my head. X times 4x makes 4x squared, x times negative 1 makes negative x. Perfect, that's what this says, so we have factored correctly. In the second group, when we do our factoring, the hope is that we'll be able to factor so that we'll take out a common factor, and what's left in the parentheses will be 4x minus 1 again. We want it to be the same as the first set of parentheses that we just created. And if we factor out a multiple of negative 3, and you do the distribution quickly in your head, you'll see that we do get this original second group again. So we have factored correctly twice, and both sets of those parentheses are the same. We're on the right track. That's the first indicator that we're doing things correctly. Then we're going to factor again. Just do a little erasing there. Okay. Now I'm going to factor here and here. The two things that I bracketed here are called terms because they're separated by this minus sign. Terms are connected by either addition or subtraction. Here they're connected by subtraction. These two terms contain a common factor, and it's the stuff in parentheses. So I usually write my common factor first, the thing that I'm factoring out, and then I'm going to write the leftovers, as I call them, in the second set of parentheses, In this case, that's going to be the x and the minus 3. And we have factored our original quadratic equation that was equal to 0. You might notice that this looks like the kind of thing that you would FOIL. The AC method helps you to reverse FOIL. The middle part of this process doesn't quite look like what you remember the FOILing process looking like, but you can definitely see that the result, if you were to FOIL and combine like terms, would give you your original statement again. Now we're going to use what we saw here, which is the zero product principle. We have two things that are being multiplied together that are equal to 0. So I'm going to take this equation over here and work on these two components over here. I'm going to take the first factor, which is the 4x minus 1, and set it equal to 0. And I'll write down the x minus 3. I'm going to set that equal to 0. And let's solve those two little equations. Adding 1 to both sides, dividing both sides by 4. That's one of our solutions, 1/4. And in the second equation, all we have to do is add 3 to both sides to get our second solution. And so, the two solutions to your original equation are positive 1/4 and positive 3. Could you check those by plugging them back into your original equation? Absolutely. I won't do that here, but you could do that. It's not really necessary, but you could. Another process that we use sometimes for solving quadratic equations is using the square root property. The thing I want to highlight for you here, and I will literally highlight it, is this. Remember that, for example, if I asked you what's the square root of 25, most of us would just answer 5, but in fact the more thorough answer is plus or minus 5, because negative 5 times negative 5 makes positive 25 again. And so when we solve this equation by taking the square root of both sides, we need to remember, well, let's start doing it. Normally I would put a little note in here that says I'm taking the square root of both sides. The square and the square root are going to cancel, leaving me with a left-hand side that says 4x minus 1. And on the right-hand side, what's the square root of 16? Be careful, don't forget the square root principle. It's equal to plus or minus 4. So this equation needs to turn into two equations. The first equation will be 4x minus 1 equals positive 4. The second equation is 4x minus 1 equals negative 4. And then I will leave you to solve those two equations on your own. Yet another process for solving quadratic equations is this process called completing the square. It's not a process that you use or need to use all that often, but every once in a while the situation kind of demands that you use this process, or you might run into a homework question that demands that you use this process. So let's have a look at it. This sort of blue or gray box here says that if we're starting with an expression like this, which is called a binomial because it has two terms, like a bicycle has two wheels, binomial has two terms. If we add b divided by 2 quantity squared, then what we will end up with is this expression, which is called a trinomial because it has three terms, and that trinomial is also a perfect square. Why is it called a perfect square? Well, would you say that 25 is a perfect square? Probably. But why would you call it a perfect square? Because 25 is the result of squaring something. This trinomial is also a perfect square because it's the result of squaring something. It's the result of, in this case, squaring x plus b over 2. So we can engineer that missing term, the b over 2 squared, by taking our middle coefficient, or the coefficient on x, dividing it by 2 and squaring it. Let's see a question that asks us to use that. Determine the constant that should be added to the binomial so that it becomes a perfect square trinomial. We know now that we can take the negative 14 as the b value. We can divide it by 2 and square it. That's negative 7 squared, and the answer is positive 49 because a negative number squared is a positive. And now, making the request a little more demanding, we're being given a quadratic equation that's already set equal to 0, and we want to solve it by completing the square. We're going to do a preliminary step in order to get this thing set up to solve by completing the square. And that preliminary step in this case is adding 5 to both sides of the equation. That way the left-hand side of the equation only has those two terms, the x squared and the x term, and it leaves us that space in order to insert our new b over 2 squared. Now let's figure out what that b over 2 squared is. We'll take the negative 3, that's our b value, we'll divide it by 2, and we'll square it. And that's equal to 9/4. The 9/4 is what we're going to add to both sides of the equation. I'm not going to write the 9/4 into that version of the equation because I want my notes to show the progress of this problem playing out. So we'll go to the next line and write x squared minus 3x. It's a positive 9/4. It's always going to be positive because we got that 9/4 by squaring something. And on the right-hand side, the number 5, I'm going to write it as 20/4, and then I'll add the 9/4 that I added to the right-hand side of the equation. If you have different colored pens, or if you want to use a highlighter, realize that the 5 is the 20/4, and if you have two highlighters, the 9/4 we added to the left-hand side and to the right-hand side. I wrote the 5 as 20/4 because on the right-hand side of this equation, I already knew, because I've done problems like this before, that I'm going to want to add those values together, and I'll need a common denominator to add with the 9/4. Let's do a little arithmetic. The left-hand side of this equation becomes x minus b over 2 quantity squared. That's part of the pattern. We saw it up here. In the problem that we're working on, this number's a 3, and what number did we add over to here? That was the 3 divided by 2, quantity squared, and the resulting expression that is a square ends up being x plus b over 2, or in this case 3 over 2, quantity squared. And there it is. Excuse me. Unfortunately, the number on the right-hand side of the equation is not a perfect square. So we have to take the square root of both sides still, because we have to solve this thing. So we will do that, square rooting the square on the left-hand side leaves us with just the x minus 3/2. On the right-hand side, we've got the square root of 29/4. A property of square rooting a fraction says that I can also write this as the square root of the numerator, over the square root of the denominator, which is nice because the square root of the denominator is a nice number. Square root of 4 is 2. You might be thinking, isn't it plus or minus 2? That's a little bit of a tricky part because you have to know when do I need to use the plus or minus and when don't I. And in this case, I've actually left something out because when I took the square root of the 29/4, I should have put in a plus or minus. So right here, let's come back and put in a plus or minus. And to the right of it, another plus or minus. And to the right of that, another plus or minus. All right, so now I'm going to rewrite this equation, only writing this equaling this, and we'll go from there. In order to solve for x, we now need to add 3/2 to both sides of this equation, and I think I'll do that over here. So we have x equals, I'm adding 3/2 to both sides, so there's the positive 3/2 appearing on the right-hand side. Don't forget to keep the plus or minus square root of 29 over 2. And very conveniently, these two fractions have the same denominator already. So we are going to now turn this into the two separate answers using or splitting up the plus or minus. Our first solution will be x equals 3/2 plus the square root of 29 over 2, or x equals 3 over 2 minus the square root of 29 over 2. I'm running off the page and right off the screen there. Since these two or four fractions have common denominators already, we can clean things up a little bit and write our final answers as x equaling 3 plus the square root of 29, all divided by 2, maybe comma 3 minus the square root of 29 over 2. If you're doing homework online, which a lot of us are, you'll probably have to enter your answer online for a question like this as two separate values separated by a comma. So make sure that you don't have any additional spaces that you're not supposed to have depending on what software you're using, but these are the two solutions that you want to enter. If the software you're using has a plus or minus button that you could use, then maybe you only have to answer one of these and just change the plus to a plus or minus sign. But you probably don't want to answer like this. You do want to write it as one fraction. And that's solving by completing the square. In case you haven't seen enough methods for solving quadratic equations, of course we remember the quadratic formula. If you haven't committed it to memory, my recommendation is commit this to memory, at least until you're finished with your algebra courses, because if you run into a quadratic equation that is not factorable, this is, in my opinion, your best choice for trying to, or for solving, a quadratic equation. So we'll solve this one using the quadratic formula. Remember that this is of the form ax squared plus bx plus c equals 0. In this case, our a value is 5, our b value is 1, and our c value is -2. And let's plug those into the quadratic formula. X equals the opposite of our b value, which is a 1, plus or minus the square root of our b value squared minus 4 times our a value of 5 times our c value of -2, all divided by 2 times our a value of 5. Notice that all of these numbers that I'm plugging in for a and b, that I plugged them in using parentheses, especially like the c value of -2, especially when you're using a negative value and plugging it in. Those parentheses are important, especially if that was the number that we had to be squaring. The 5 next to the -2 over here, if you didn't have parentheses around these, you might get confused and it would look like 5 minus 2 or 4 times 5 minus 2. So this just helps to make sure that we're doing all of our orders of operations in the correct order. From here on out, it's just arithmetic, so let's start cleaning this up. X equals -1 plus or minus the square root of 1 plus 4 times 5 is 20, times 2 is 40, all divided by 10. This is not going to be a nice answer. It would have been nice if this was like 49, so we could have taken the square root of it, but that's not always going to happen, unfortunately. So we end up with -1 plus or minus the square root of 41 all over 10. And here is your pair of solutions that you want to probably type in if you're online as 2 separate answers separated by a comma. Those solutions are -1 plus the square root of 41 all divided by 10, comma, -1 minus the square root of 41 all over 10. If, so this is just an aside, x equaled, let's say it equaled -20 plus the square root of 41 over 10, could I reduce or simplify this statement? Yes and no. Could I reduce this and turn it into a -2 and turn this into a gone, essentially making it a 1? And then my final answer would be -2 plus the square root of 41. The answer is no. You're not allowed to do that. Just as with multiplication, you have to distribute multiplication, division abides by the same rules, and you must distribute your division. So you can't simplify this expression right here, because while you can reduce here, you cannot reduce this, because the square root of 41 is not evenly divisible by 10. So if you can't reduce in both directions, so to speak, if you can't take both terms in the numerator and divide them or simplify them with the denominator, then just leave it as it is. In the quadratic formula, we saw that under the square root symbol is b squared minus 4ac. That expression is called the discriminant. And if your discriminant turns out to be a nice number like 49, as I mentioned before, then the square root of 49 is 7, and these two solutions would have turned out to be a lot nicer. You would have had -1 plus 7 divided by 10, -1 minus 7 divided by 10. You could have simplified both of those numerical answers. Those answers would have been rational numbers. Fractional numbers, okay? But they're rational. They wouldn't have any square roots in them still. And that's one of the scenarios where the discriminant, the stuff under the square root symbol, is a positive value. So whether it's a number that's nice and that can be square rooted, or if it's a positive number like 41, which is not so nice because you can't take the square root, either way, you're going to end up with a real number. Two real numbers, in fact, because of the plus or minus symbol. Right up here, plus or minus the square root of 41, plus or minus the square root of a positive number, gave us two real answers. Now, if the discriminant had turned out to be 0, let's go back again. If the discriminant had turned out to be 0, then we would have had -1 plus or minus the square root of 0 over 10, which equals -1 plus or minus 0 over 10. Well, what's -1 plus 0? -1. What's -1 minus 0? still negative 1. So while for a long time it was looking like we were going to have two solutions, if your discriminant's equal to 0, then this thing turns out to really only give you one solution. And that's what this table on the next page is saying, is that if your discriminant turns out to be 0, then you're only going to have one solution. It's called a repeated solution. It's like you still have two answers, they just happen to be the same answer. And that's also a real solution. If you'll bear with me, I'm going to slide back up here again. This number, negative 1/10, is a real number. In the previous section, we talked about complex numbers and imaginary numbers and square rooting negative numbers. And that's what happens that's what you run into if your discriminant is less than 0, then you end up having to take the square root of a negative number. Whether it's a purely imaginary solution or if it's a complex number, a plus bi, a complex solution, those two solutions you would end up with would not be real. They'd be imaginary. Visually, graphically, we see some nice demonstrations of examples, very generic examples, of what's happening graphically with these three different scenarios. A quadratic equation, if you graph it, because of the x squared, is going to turn out to be a parabola. Sometimes it's wider or narrower or it's upside down, but it does turn out to be a parabola. And when you take that parabola and you set it equal to 0, what that 0 really is representing is a y value of 0. And you can see on this graph that these 2 points have a y value of 0. The x coordinates of those 2 points are your solutions to the equation when your quadratic equation is set equal to 0. So here you've got two solutions, two x-intercepts. Here, where we had the repeated solution, where you had a discriminant equal to 0, you only have one solution, or one x-intercept, one x value that if you plug it into your original equation will give you an output value, or a y value of 0. And it is possible to design a quadratic equation, and you will definitely run into quadratic equations that when you set them equal to 0, or when you try to determine what x value could I plug in so that I get out a y value of 0, it's possible that there aren't any options. No x value plugged into your equation will give you out a y value of 0. And graphically, this is what it looks like. It could be a parabola facing or a concave up, hovering above the x-axis. It could be a parabola that's concave down, where the entirety of it is below the x-axis. So always trying to, when possible, I love relating the algebra to something graphical because some of us can visualize this stuff more easily than we can just tolerate these kinds of algebraic statements. I know they can seem kind of arbitrary sometimes. Alright, so here we want to compute the discriminant given this quadratic equation and determine the number and type of solutions. So let's calculate the discriminant. The discriminant is b squared minus 4 times a times c. In this case, that is equal to 11 squared minus 4 times 2 times negative 6. I'm not going any further because I know that a negative times a negative is positive, and I'll be adding that positive to this squared number right here, which is definitely going to be positive. So this is equal to positive plus positive, which equals positive, which is greater than 0. So you can calculate, you can figure out what this number actually is. I don't care what it is specifically, I care where it is. I care that it's greater than 0, equal to 0, or less than 0. And in this case, it's greater than 0. And since it's greater than 0, that was supposed to be an arrow. And sometimes my pen does not play nice. There we go. Because the discriminant is greater than 0, we know that there will be two real solutions. So your answer to example number 5 is 2 real solutions. Determining which method to use, you should read through this. With experience, you'll be able to do those couple of preliminary steps on your quadratic equations so that it's equal to 0, and then you'll be able to decide what to do. I highly recommend looking through this table because when you're working with an equation in this format, that's what we've been working on in the previous examples. If your a value in particular is something other than 1, then I would say use the AC method. If your a value is a 1, you might be able to just sort of rough out what the thing's going to look like and drop an x value in here and then sort of guess and check your way into these numbers, or use a little bit of reasoning, a little bit of problem solving, imagining foiling the thing out in your head and combining like terms in order to get the correct b and c values. But if you struggle with that, you can always do the AC method, and it's the same number of steps every time. If it's factorable, it's going to get you there. In this second sort of scenario where you don't have a c value, or your c value is equal to 0, you don't really need to use the quadratic formula. What you would probably want to do is factor out an x. And what does it say over here? So these are really nice illustrations. So for this second scenario, notice that we don't have a constant value. There's no c value. So all they did here was factor out a GCF, a greatest common factor, and then use the zero product principle. They factored out the 3x. That left them with leftovers of the 2x plus 3. Now you've got the product of two things equal to 0. A times b equals 0. So they set a equal to 0, they set b equal to 0, and then they solved those little equations. That's really nice. I like when that happens. Those problems are much faster to solve. This scenario is even easier. Subtract that c value over to the right-hand side. Divide both sides by a, and then take the square root of both sides. And go check out that example over there. And don't forget to include your plus or minus symbol when you take the square root of both sides. Using the square root property again, if the left-hand side of your equation is already set up as a square, then just immediately take the square root of both sides. That's exactly what we did when we worked with solving a quadratic equation by completing the square. Except the right-hand side of our equation in that case I think was a 41, which was lousy. Here it's a 5. It still stinks. You can't take the square root of 5. So you end up with a radical in your answers. That's okay. And if it can't be factored, then your best bet is to use the quadratic formula. And that'll take you to your 2 solutions or your 1 solution, whether they're real or imaginary. So those are different scenarios to be mindful of, and as you're going through a homework assignment, be aware that you could run into any of those, and you will. Your homework assignments are going to include a variety of different types of equations, so make sure you choose the correct method. I wouldn't even hesitate to make some flashcards for those different kinds of methods. I would put maybe if you look at the top right corner of your screen, you put an equation like this on one side of your flashcard, and then put some notes, something like this, on the other side of the card. On the other side of the card I might write, since my a value is 3 and not 1, use the AC method. And then on my next flashcard, or whatever digital version of flashcards you want to use, put this second equation and put sort of a brief sketch of the solution process, or put the entire solution process on the other side of the card. And have a friend sort of check your work as you talk through the process, or write out the solution process on a piece of paper and then flip the card over and check your own work. But those are the different scenarios you want to look out for when you're working with quadratic equations. And we're going to look at some other examples of similar problems in the next section. See you there.